Today we're going to be answering prove there are no integer roots of any polynomial questions, which may sound a slightly strange thing to do a video on, but in actual fact these questions are becoming more and more common in exams. So basically the idea is let's have a look at this first question here. They give you a polynomial and they have to tell you to prove that it has no integer roots by some method. In this particular question here they say prove by contradiction, but we're going to do 4 questions and they're all 4 slightly different and we use a couple of different methods. So let's go on this one anyway. So basically what we do on this one, as we're proving by contradiction, we've already done a video on proving by contradiction, so if you want to have a look at that, the link is in the description to this video. But anyway, basically there are 3 steps. So step number 1 in our proof by contradiction is that we assume the statement is not true, i.e. we assume that there exists some integer alpha contained in the integers such that, sorry, let's get a bit more space, such that as it is a root such that 3 alpha cubed add 6 alpha add 2 equals 0. So that's step 1. Step 2, we now have to show that this leads to an impossibility. Okay, so let's take the factor of 3 out. So that's 3 alpha cubed add 2 alpha equals minus 2. Now, if alpha is contained in the integers, that implies alpha cubed add 2 alpha is also contained in the integers, because if you cube an integer you get an integer, and if you multiply it by 2 you get an integer. And so therefore we have that 3 alpha cubed add 2 alpha is a multiple of 3, but minus 2 is not a multiple of 3, hence we have a contradiction, because it is impossible that 3 times something, given that that is an integer, equals minus 2. And therefore our conclusion is, therefore, because of the contradiction, the equation 3x cubed add 6x add 2 equals 0 has no integer roots. And by the way, often on this one here, basically, as long as you can take a factor out of this bit here, and that factor is co-prime to this number here, then this will always work, this trick. So, I mean, you know, for example, this could be 5 add 10, and we could have taken the factor of 5 out, and again we'd have 5 times some integer equals minus 2 or minus 3 or minus 4 or whatever. This method always works for there. So now we're going to have a look at question 2 where this method doesn't work and we have to do something else. So let's have a look at question 2. Okay, this one, proved by contradiction the equation, this one has no integer roots. We can see that we can't use our little trick here. Okay, but we're still going to use by contradiction. So basically we are first of all going to assume that the statement is not true. That's always our first step on proving by contradiction. So therefore we assume there exists an alpha contained in the integers such that it is a root, i.e. 3 alpha cubed add 8 alpha squared minus 1 equals 0. That's just sticking the root into there. Now what we're going to do is we're going to take alpha squared out of here, and that leaves us with 3 alpha add 8 equals 1. Now, if alpha, again, we use the same logic as before. If alpha is contained in the integers, then alpha squared is obviously contained in the integers, and 3 alpha add 8 is obviously contained in the integers. And there are only, so therefore this bit here is an integer and this bit here is an integer, and there are only 2 sets of integers which multiply together to get 1, i.e. minus 1 and minus 1, or 1 and 1. And so therefore alpha squared equals minus 1 and 3 alpha plus 8 equals minus 1, or alpha squared equals 1 and 3 alpha plus 8 equals 1. They're the only possible 2s. Now obviously alpha squared can't equal minus 1 because alpha is an integer, a real integer, so we can get rid of that one. So basically that just leaves this. So either alpha is plus or minus 1 from this, and alpha equals minus 7 over 3. Well, to start with, that's not an integer. And secondly, we have a contradiction here because it can't equal both of those. And so therefore our conclusion is, because we found ourselves an impossible contradiction, hence our conclusion is therefore that equation 3x cubed add 8x squared minus 1 equals 0 has no integer roots. Okay, so that's question number 2. Let's have a look at question number 3. Now this time we can't really use either of the two tricks above, and we're going to use modular maths. Okay, so basically what we're going to say, if there is an integer solution, alpha contained in the z, there's an integer solution to this, well then basically we know that 7 alpha to the 5 minus 23 alpha squared add 2 alpha minus 8 equals 0 by definition, because that is a solution to this equation. But also that means that 7 alpha to the 5 minus 23 alpha squared add 2 alpha minus 8 is equal to 0 mod anything by definition. And so all we can do, if we can find some mod whereby this cannot possibly be true, then we have proved that the equation has no integer roots. Okay, so now let's just have a look at Fermat's little theorem, because we're going to use that. So Fermat's little theorem states that a to the power of p is equal to a mod p for any prime. For any prime p, for prime p, any prime p, okay. Now, so that basically means, if we look at mod 3, we can say that a cubed is equal to a mod 3 by Fermat's little theorem. And so therefore, if we multiply both sides of this by a squared, we also get that a5 is equal to a cubed, which we've just shown is equal to a mod 3. Okay, so basically we can rewrite this equation here using what we've just found here. We can rewrite, well, alpha to the 5 becomes alpha, so we can rewrite it as 7 alpha minus 23 alpha squared add 2 alpha minus 8 equals 0 mod 3. And therefore we can write that 7 alpha add 2 alpha is 9 alpha minus 23 alpha squared minus 8 is equal to 0 mod 3. Okay, now let's have a look at the numbers. Well, obviously 9 mod 3 is 0, so that basically disappears. That's 0. Minus 23 mod 3 is plus 1, so that becomes plus alpha squared. And minus 8 is the same as minus 2 mod 3, so that equals 0 mod 3. And so therefore we have that alpha squared is equal to 2 mod 3. Now there's a problem with this. Let's have a look at the 3 possible values of alpha mod 3. Well, it could be 0, 1 or 2. So alpha squared can be therefore 0, 1 or 4, which is basically and alpha squared mod 3 is equal to 0, 1 or 1. So regardless of what value alpha takes, modulo 3, it is impossible for it to equal 2. There is no integer in the entire world where alpha squared equals 2 mod 3. And therefore, we have ourselves a contradiction. And therefore, this equation cannot be true for any alpha contained in the integers, and therefore it has no integer roots. And that's question number 3. Okay, so finally, let's go to question number 4. This is my favourite question. This was the one on the thumbnail. What I like about this question is it seems to be impossible that you can solve it, but in actual fact you can. And we're going to solve this by 2 methods. Okay, so first of all, let's solve it by the polynomial factor theorem. That's the first one. Okay, so the polynomial factor theorem says that for any polynomial with integer coefficients, any polynomial, by the way, of order anything, it doesn't matter what the order is, if it's got integer coefficients, then a minus b divides p of a minus p of b. Okay, so basically what we can say now is if there is an integer root here, let's assume that there is an integer root. Let's call it alpha. Let's call alpha being the integer root. Well, then p of alpha, by definition, as it's an integer root, is going to be equal to 0. Okay, so basically we can then use this here. Using p of 2 is 5, which we're given here. We have, therefore, that, using the polynomial factor theorem, we have that 2 minus alpha divides p of 2 minus p of alpha, and p of 2 minus p of alpha is 5, take away 0. So therefore, 2 minus alpha divides 5. And using p3 equals 7, which it also tells us, by the same logic, using the polynomial factor theorem, we have that 3 minus alpha divides p of 3 minus p of alpha, which equals 7 minus 0, which equals 7. So therefore we have that 2 minus alpha divides 5, and 3 minus alpha divides 7. So the only integer factors of 5, the integer factors of 5 are minus 5, minus 1, 1 and 5. And the integer factors of 7 are minus 7, minus 1, 1 and 7. So therefore we know that 2 minus alpha is either equal to either, oh no, that's not very good maths, either minus 5, minus 1, 1 or 5, and 3 minus alpha is equal to either minus 7, minus 1, 1 or 7. And both of these have to be true. Okay, and therefore we know that from the first one here, alpha is got to be contained in the set minus 3, 1, 3, 7, and from the second one here, alpha has got to be contained in the set minus 4, 2, 4, 10. Now the problem is that there are no common elements in these two sets, and alpha therefore can't be contained in this and in this because there isn't anything that is contained in both of those sets, and therefore we can conclude that there is no integer solution to this polynomial. That's method 1. Okay, now method 2 is pretty clever. So let's just have a look at method 2. So basically we have that p2 equals 5, and we have that p3 equals 7. Okay, so now let's look modulo 2. All right, so modulo 2, 2 mod 2 is 0, so p of 0 is equal to 1 mod 2 equals 1 mod 2, and p of 3, well 3 is 1 mod 2, so p of 1 is equal to 1 mod 2. Okay, well hang on a sec, so whether we are looking at 0 or 1, they both come to 1 mod 2. But all integers mod 2 are either 0 or 1, so no matter what integer we put into this polynomial, it will be an odd number, and therefore it can't be 0. And so therefore there cannot be any integer solution to this polynomial, because regardless of whether the number is odd or even, the polynomial shoots out an odd number. So that's a really nice, neat proof using modulo maths. Thought I'd put that in at the end. Well, I hope you found this useful. Normally the questions are proving by contradiction, and then you just have to be really careful to make sure that you write your answer properly. But sometimes they give you a choice, and you can use modular maths if you want to. I hope you found this useful. I hope you get one of these questions on your exam. I hope you get full marks on it. If you've liked this video and found it useful, please like it and subscribe to the Gresty Academy YouTube channel. Thank you.